pretty disappointing.
Okay. Hi, Antronic. Can you hear me?
Yep.
Oh yeah, what genre?
All right.
Hey, Antronic, are you able to hear me?
Hi, Justin. Yeah, I can hear you. I cannot see you though.
Okay. Yeah, our room computer is not working, so I'm just connected to my own computer. I could turn my camera on, but it'll just be a view of my face, maybe at like an up angle. Right.
Yeah, no worries. As you wish.
Okay. All right. Thanks for calling in.
Yeah.
It's coming.
Oh,
Yeah.
well, I'll wait for people to sit down.
That's what you just want to give us some stuff.
Yes.
Wait, you can contribute. You can educate us on what a proper joke should be.
Yeah.
Okay.
Why can't you hear a pterodactyl pee?
It's silent.
It's silent.
It's silent. That one's never.
But the, they could-
You know, high stuff like at the start of last semester. Well, was that not you?
I think the last time I gave one was last year.
Oh.
Yeah, it is.
This is the spring because we don't have has fell yet.
We will get nice snack this fall.
Probably not. I'm tired.
Kind of open a new grad student take over for you.
Yeah, it's another way.
All right, should I start? Okay. Yeah, thanks everyone for coming. This is actually sort of a practice talk for a talk that I'm going to be giving at Space Telescope on Friday. And so fair warning, I haven't really practiced this that much, but you know, I'm definitely open to any feedback from people. It's not like a formal seminar or anything like that. It's a pretty informal thing. Yeah. Thanks all for coming. And you know, today I'm going to talk to you about some of this work that I've been working on for the past year or so. This survey called the Disks In Scorpius-Centaurus Survey, or Disks. And the goal of this survey is to sort of have this collection of benchmark debris disk systems in the scattered light regime. Okay. Now, why does that not advance the slide? There we go. Okay, so I'm going to start with a bit of a crash course in debris disks. So debris disks can be sort of thought of as these sort of dusty remnants of the planetary formation process. Our own solar system actually has a few of these types of debris disk systems or components. So this is just like a nice sort of schematic diagram showing, you know, what sort of different debris disk components may look like. The debris disks that people are probably the most familiar with are the asteroid belt and the Kuiper belt. So in this graphic, these are sort of the inner belt and the outer belt. But we also have we also have other dust components in the solar system as well. So like the Oort cloud, for example, that's the most analogous to this sort of halo of dust that's sort of outside the outer belt. Planets have their own dust belts. So like Saturn, for example, and Jupiter. We also have various comets, Trojan asteroids, and the zodiacal light, which is sort of this interplanetary dust that is sort of all throughout the solar system. Okay, so what is the sort of evolutionary process of debris disks? So, when you have really young stars, they often have these really gaseous and dusty disks around them when they first sort of form. These are protoplanetary disks, and they tend to have this really flared shape. And over time, over relatively short time scales, you get a lot of accretion and UV energy from the star that can evaporate a lot of this gas material, and the dust starts to accrete as well, until eventually you lose most of that gas, and your dust starts to sort of settle into a disk plane or so, or a disk midplane. And so this final stage is what we typically call the debris disk stage, where you've lost most of your gas from the star formation process, and you're mostly just left with dust and planetesimals left over. Okay, so how do we actually observe debris disks? Well, this is sort of getting into the history of how debris disks were sort of first inferred or first detected. So we didn't actually directly image them. We sort of inferred their presence by noticing that some stars have this excess of emission at mid and far infrared wavelengths. So this is sort of nominally considered the first detection of a debris disk around Alpha Librae or Vega. And you see here on the left is the special energy distribution, which is essentially just the energy or the flux from the star as a function of wavelength. And you see this excess of emission at these sort of mid to far infrared wavelengths. And you wouldn't expect this for a star like this because stars are mostly bright at near infrared wavelengths or visible wavelengths, not at the mid or far infrared. Now, it's not actually a shell, really, that is around Vega. It's more like you have these dust belts. So on the right here, this is an image taken with ALMA of the same debris disk in this system, showing that you have more of a disk-like shape around the star rather than like a shell per se. So measurements have definitely improved since this. And so nowadays you can get multiple measurements across multiple wavelengths to measure the spectral energy distribution and sort of infer the properties of a debris disk. So I believe this is actually an SED of Beta Pictoris. I may be wrong, but Beta Pictoris has this sort of really iconic edge-on debris disk. It's really bright, and you see a lot of that in these sort of red points at these mid and far infrared wavelengths. And you see this excess emission because the dust grains in the debris disk are absorbing light from their host star and then re-emitting that light in the mid to far infrared wavelengths. So that's why you get this excess of thermal emission. And a quantity that we typically associate with debris disks is the fractional infrared excess, or LIR over L star, because it's essentially telling you, okay, like how much more light or how much more flux are you getting from the star at these mid to far infrared wavelengths relative to the flux that the star would be emitting at those wavelengths if there wasn't a debris disk. So it's kind of giving you an idea of the sort of amount of dust that may be in a system, and also the location of this sort of peak that you see here can tell you a bit about the location of that dust relative to the star. Because this, say you fit like a black body to this. This would tell you sort of the temperature at which these dust grains would be emitting at, and that is sort of directly related to the orbital separation of those dust grains. Okay. Great. So, so SCVs can already tell us a lot of info about these systems, but it doesn't necessarily tell you about some really like finer details or smaller scale structures. And so to that, we turn to imaging. And so nowadays, we actually have pretty powerful instrumentation to actually resolve the dust components in these systems at multiple wavelengths. And, you know, looking at these systems in multiple wavelengths is really helpful because different wavelengths are sort of sensitive to different sizes of dust grains in the debris disk. So at long wavelengths, yeah, like I said before, your dust grains absorb energy from the host star, re-emit that energy at these longer wavelengths in the form of thermal emission. But at short wavelengths, it's actually more efficient for incident photons to scatter off of the dust grains that are of that size, so like micron size or submicron size. And so this is the Fomalhaut system at different wavelengths, so HST, JWST, ALMA. And for my work, I'm actually going to focus on the scattering regime or the short wavelengths. And the reason why I like the short wavelengths or the scattering wavelengths is because the fact that we even have scattered light detections of debris disks is already unusual. And this is because, you know, at the ages where we detect debris disks around these stars, you wouldn't expect a lot of these micron or submicron sized dust grains because there should have been forces that would have, you know, expelled those dust grains, you know, well before the age that we, you know, well before the age that we see them at, because they're very small, right? So they're more subject to effects like radiation pressure, so like being blown out of the system, and they're also subject to accretion or Poynting-Robertson drag. So that pulls the dust, you know, into the star. And so the fact that we even see debris disks at these scattered light wavelengths is unusual. So something must be happening to replenish the supply of small dust grains in these systems. And, you know, one of the possible things that could be replenishing these dust grains are ongoing collisions between larger dust grains that may be caused by, you know, interactions with perturbing forces like planets. So you could have planets in a system that are perturbing these larger dust grains, causing them to collide with each other and create these smaller dust grains as a result. So that's why I really like these sort of short wavelengths here. And images can tell you a lot about debris disk systems. So, you know, you can actually measure the direct sizes of the rings. You don't have to infer that from an indirect measurement. You can also get a sense of the vertical structure. If you have like an edge-on system, and vertical structures can tell you more about some of the perturbing forces that may be in a system. And if you identify asymmetries in debris disks, that could be evidence for perturbing forces as well, like planets. So this is the HD-106-906 debris disk system, and it has this asymmetric and eccentric debris disk. So you see evidence of like a warp right here. And there's actually been dynamical modeling to show that this exterior substellar companion, HD-106-906b, which is on an eccentric or is on a mutually inclined orbit relative to the debris disk, could actually cause that asymmetry that we see. From the scattered light imaging as well, you can also learn a bit about some of the intrinsic dust grain properties too. So one thing that's particularly interesting is the scattering phase function, which tells you the distribution of scattering efficiency as a function of deflection angle. And I'll get more into that a bit later. And all of this can be used to sort of infer properties about the composition of the dust grains, along with the sort of distribution of the different grain sizes in a debris disk as well. Something else that's really interesting is polarization. So in the scattering regime, dust grains not only scatter the incident photons, they also polarize them linearly. So you can actually measure that polarization And from those measurements of polarization, you can also infer properties about the distribution of dust grain sizes, along with their compositions. But, detecting these debris disks in the scattered light regime is challenging, because they are of order 10 to 100,000 times fainter than their host stars, and they're at pretty small separations relative to their host stars as well. So to do this, you really need to be able to do high contrast imaging, blocking out most of the stellar lights, most of the on-axis stellar light, so that you can actually make out these types of structures. So a lot of my work has been using the Gemini Planet Imager. This was a high contrast imaging instrument that was installed at the Gemini South Telescope up until about 2020. It mostly operated in the near infrared, so J, H, and K wavelengths, sort of the smallest separation from which you could actually make out any, structures or detections. This is called the inner working angle, was about 100 milliarc seconds or so. And it had a spatial resolution or plate scale of about 14 milliarc seconds per pixel. Like a typical high contrast imaging instrument, it made use of adaptive optics along with a coronagraph. And so generally, GPIE could achieve contrast down to 1 million or even 10 million times fainter than the host star at separations within an arc second or so. Another unique feature about GPIE was that it was an integral field spectrograph. So you can get simultaneous imaging and spectroscopy of your images. And sort of that same hardware also allowed them to do integral field polarimetry. So you can get simultaneous orthogonal polarization images of your system. And then eventually, you build up enough rotation angles and you can generate what's called a Stokes vector image of your system. So the primary sort of science goal for GPIE was to detect and image and characterize young Jovian exoplanets at these near-infrared wavelengths. Some of you may know that high contrast imaging instruments did not find a lot. They did not find a lot of these young exoplanets because it turns out they're a little more elusive than we thought they would be. But what GPIE was able to do was detect and image a lot of debris disks. And so these are all H-band polarimetric images of debris disks that GPIE was able to image. And many of these systems were actually imaged for the first time with GPIE in these scattered light regimes. So this is a figure that I think anyone who works on short wavelength debris disk imaging, they know this figure because this was sort of the first comprehensive survey for scattered light debris disks ever done with a high contrast imaging instrument. Okay, so now we're going to sort of get into the motivations and the goals for the work that I'm about to show you. So, okay, we have a lot of resolved scattered light detections from GPIE of debris disks. What do we do now? I think having this many detections sort of lends itself to having a sample in which to investigate trends in the properties of these types of systems in this regime specifically. Why is this important? Well, this really helps ground and inform theoretical models that predict things like planetary system architectures, dynamics, evolution, and formation, particularly in the context of the smallest dust grains, right? Because all of our scattered light images are telling us about the smallest dust grains in a system. And this also helps us contextualize individual debris disk detections in sort of the broader story of planet formation. I just wanted to give a shout out to some of these recent papers that have started to do this, right? Like we're sort of in the new era where we have all of these images of debris disks, and great, but it's really hard to talk about the individual properties of individual systems because you don't have a good sort of grounding for, what is sort of like a ground truth, right? For what you're dealing with. So, we want to be able to do these like population type studies because we want to know, okay, like what are trends, that we expect to see across these systems, and what are trends that we can base new detections of new systems on, in order to understand what may be going on in those systems as well. But there are already some challenges when it comes to trying to construct this sort of empirically grounded benchmark sample. So the first is having to contend with scattering phase functions. And I'm going to get into this a little more later in the talk, but scattering phase functions kind of heck up the whole picture. They're more challenging to deal with than if you were just detecting or imaging these disks in thermal emission. And I'll explain why later. But another issue is that, population type studies are really dependent on a sort of uniform or homogeneous sample, right? So the question that I'm asking right here is, is the sample of GPIE image debris disks, is it actually homogeneous? Is it actually a good sample to be able to base, whatever new detections or individual analyses off of? So I'm going to focus on this first. So I'm going to go over each of the ways where this debris disk sample may have been biased or unbiased. So let's talk about the unbiased things first.
Justin?
Yeah.
Here you go. When you say small dust grain, can you put a number to what that means?
Yeah. So think like smaller than a few microns or so in size.
Okay.
That is sort of
Yeah,
it's not a hard cutoff, but there's sort of a transition to when you get to longer wavelengths, you're observing more of the larger size dust grains, and for those larger size dust grains, it is more efficient to absorb the incoming radiation from their host star and re-emit that, versus for the smaller size dust grains, it's more efficient to scatter those incident photons rather than absorb and re-emit. There may still be some level of absorption and re-emission going on, but we typically consider the effect to be dominated by scattering. Okay. Yeah. So some of the ways in which the sample was unbiased, well, they were all taken in the same type of observing mode, and it was all with the same instrument, right? So H-band, 1.6 microns, polarimetric imaging, all from the same instrument. So, you don't have to worry about like differing systematics, like between different instruments. You don't have to worry about sort of a correction factor between different wavelengths, or whether or not you're imaging in polarized intensity or unpolarized total intensity light. So it's all uniform in that sense, which is great. And this survey, which ended up looking at close to around 150 stars or so, a subset of that sample was sort of drawn by identifying high infrared excess systems that were unresolved. And basically how the sample was built was, okay, I want to look at the highest infrared excess systems, and they need to satisfy, these other requirements as well. So distance is important because the bigger your distance, the smaller your disk likely is, right, spatially. And so you wouldn't be able to, see much of it, right, if it was too far away. And the distance cut is, roughly within 150 parsecs or so. Age, because if your debris disks are too old, you likely won't be able to detect them because they probably wouldn't have as many of the smallest dust grains remaining in scattered light. And then there's also a sort of magnitude restriction on the host star, because in order for GPIE to actually work, you need a pretty bright star in order for it to do its internal sort of AO correction, and do high contrast imaging. Great. So a big part of the 150 or so target sample was sort of drawn by identifying stars that satisfied all of these criteria. And, it wasn't just the sample itself, but even the way we prioritized, when we would observe certain targets was done with this very complicated metric that predicted the likely surface brightness of those systems based off of various factors. I'm not going to go into the various factors because it was a very convoluted process. And a bit of a spoiler alert, it didn't really end up mattering that much. But if you're interested in that, feel free to ask me about that a bit later. Okay, so these are what I consider sort of the unbiased facts about the sample. But now let's get into some of the ways in which the sample was biased. So I said a subset of the target sample was drawn from identifying systems that satisfy this criteria, but that's just a subset. The remainder of the sample I would consider handpicked, meaning that there was a good chunk of sample targets that were just selected because they had been previously detected or resolved in scattered light wavelengths, particularly with instruments like STIS or NICMOS on HST. So, in that way, they may or may not have satisfied those criteria, but we said, well, an instrument was able to detect these before. So let's just look at them because we can probably detect it as well, right? Why this is kind of a problem in terms of making the sample very biased is that ultimately about half of the 30 or so debris disks that GPIE was able to detect were these handpicked systems. So half of the sample, it was not selected from satisfying all of these criteria, right? It was just like they had been previously resolved and we detected them. So, you can argue that that actually makes the sample very biased, right? Because you're not sufficiently probing the regimes of your target sample criteria that you would like to probe.
But then you can go back and check how many of those sources would have satisfied the criteria, though, right?
Right, yes. So you can do that, but then there are some other differences that arise as well. So a big one in particular are ages. So there are at least a couple of systems in here where from the detected sample, the previously detected sample, where we would not have included in this criteria sample because they were too old, but we were able to detect them anyway because we knew that other instruments were also able to detect them. So there are some subtleties to that. Ultimately, at the end of the day, we're still kind of dealing with small number statistics. So in some ways you can't avoid all bias, right? But this was definitely a big thing that really limited us in terms of being able to characterize all these systems together in a uniform way. Another bias is that pretty much all of the sample, or most, I would say like 90% of the sample, were all detected around A and F spectral type host stars. And that's not super surprising. I mean, detecting debris disks around later spectral types like Gs, Ks, and Ms is just pretty rare in general. But yeah, this is just an inherent bias that's also built into the sample. Okay. And lastly, most of the systems have very high viewing inclinations, meaning they're close to edge on. So they kind of look, flat. They don't look like a ring, right? And this actually ends up being a detection bias because the way that the scattering properties of these systems work is that they mostly scatter photons in the forward direction or close to the forward direction, meaning that debris disks that are closer to edge on end up being brighter than debris disks that are away from edge on. And so we have a detection bias there, right? We're more easily able to detect the systems that are close to edge on. Okay, so this is sort of summarizing what's unbiased and what's biased about the GPIE debris disk sample. But is there a way that we can salvage this and create a more unbiased sample as possible, or as much of an unbiased sample as possible? And the answer to that kind of lies in a sort of subset of the sample of debris disks that were detected around stellar members of the Scorpius-Centaurus OB association. So it turns out about half of the 30 or so debris disks that GPIE was able to image and detect are actually members of the Scorpius-Centaurus OB Association. And the Scorpius-Centaurus OB Association, or SCOSEN, it is this sort of star. It's this really young cluster of stars, about 10 to 20 million years or so in age. It's about 100 to 150 parsecs away. And what's really nice about SCOSEN is that it's sort of at this age where we expect debris disks to be at their brightest, or debris disks to have the most amount of dust content, in their lifetimes. So that's really nice. And just the fact that you have all of these detections means that, you can sort of eliminate age, right, as a factor that could be affecting, how bright or the properties of your system. And they've, all of these stars have also formed in a similar environment as well. So you get rid of that degeneracy too. And I mean, SCOSEN is already great because, like I said, most of the debris disks that we've detected have in scattered light have been in SCOSEN, and SCOSEN also has a ton of protoplanetary and transition disks as well, so much younger systems. And we also have some detected substellar companions too. So, overall, SCOSEN is great because it's really a rich environment in which to sort of investigate the properties of young planetary systems at sort of different stages in evolution. Great, yeah. So like I said before, a lot of detections have been in SCOSEN. And even better, most of the detected debris disks that we have in SCOSEN were not drawn from this hand-picked previously detected sample that I was talking about before. And so most of these actually just satisfied those sample criteria that I was listing before in the sort of unbiased column of the sample. And so in total, when you combine debris disk detections from multiple instruments, so GPIES and Sphere, GPIES and Sphere have actually looked at almost half of all SCOSEN systems that are above this sort of fractional IR excess threshold. And this 2.5 times 10 to the minus 4 number is special because this was sort of determined to be the rough lower limit of what high contrast imaging instruments could detect. So like if a system had an infrared excess, roughly above 2.5 times 10 to the minus 4, there was a really good chance that you would detect that system in scattered light with a high contrast imaging instrument, so like GPIES or Sphere.
Maybe I don't understand this, but the excess, that's a small factor greater than what the star would be. I would imagine it would be like 10 to the 4 times more just based on your earlier plot.
Well, so it's a bit confused. So it's LIR over L star. So it's the ratio, right? So the ratio in which you have like right, okay. How should what is the best way to describe this? So yes, it is a number less than 1.
Yeah.
Right. But the way it's written, LIR over L star is
Like 1 minus that thing.
yeah, I mean like one divide like
Yeah. Okay.
It's that's kind of maybe the better way to think of it. I mean you're looking at the ratio of what is the I mean there are also some subtleties about polarimetric versus whatever, but yeah.
Is this just like a normalized intensity thing? Like if your star has a brightness of 1, then if your disk has a brightness of 2.5 to the minus 4, you see it?
Yeah, I mean, yeah, kind of. Yeah, I mean, I'm kind of struggling with a better explanation. So, because this is just so like drilled into me. But yes, I mean, essentially all you really need to know is that if you're above this threshold, that is a lot of dust content in the system. And this number is important because from that big survey that GPIES did, they found that we could not detect any systems if they had an infrared excess level less than that value. essentially. That doesn't mean that they detected 100% of systems with excess levels above that value. But it does mean that they detected 0% of systems below that value, right? So it's probably closer to like 90% of systems detected above that excess value. And so that is what they're defining as their loose detection cutoff.
And another just question about that. Is this quantity defined for a waveband or over like an integrated SED?
It's an integrated SED,
Okay.
yeah. So it's bolometric.
Okay.
Yeah. So in total, GPIE and Sphere have looked at about half of SCOSEN systems that are above this infrared excess threshold, and spectral types, earlier than K, but that's related to the magnitude restriction. And overall, it's had a detection rate of close to 80%. So 80% of the systems of the 50% of SCOSEN systems observed have been able to be detected. So, to give you a comparison, the remainder of the sample, so the non-SCOSEN systems, have a detection rate closer to about 50% or less, or so.
So.
Yeah.
Inclination pretty much explain why you're not getting the other 23%.
Yeah, so I'll get into that a bit later.
Okay.
But yes. Great. Yeah, so the idea here is that, okay, the SCOSEN sample by itself could be a promising unbiased sample for us to use. And so this is what motivates this survey, or disks. And so, with any sort of sample of benchmarks, you always like to have more, right? Because there's power in more numbers. So, so this survey is going to build upon the sample by trying to detect more of these systems, specifically in SCOSEN. And we're trying to complete this sample, right? So we're about 50% of SCOSEN systems observed. We want to increase that number. And so for our sample criteria, it's going to be defined in a similar way as what the GPIES survey did, except now we're going to institute an excess cutoff. So GPIE looked at lower excess systems, but now we're just going to cut it off at this sort of detection threshold. But otherwise, it's going to follow much of the same criteria as what GPIE did. Now, in terms of our observations, we ended up looking at about 7 stars with GPIE H-band polarimetric imaging before GPIE was taken off Gemini South. Again, these mostly covered A through F spectral types, and sort of the range of IR excesses of our stars covered this sort of pretty high excess, so like 2 times 10 to the minus 3, down to the detection limit or so. We'll call 2.5 times 10 to the minus 4 the detection limit. And it also happened that 3 of our systems were also detected at ALMA millimeter wavelengths, so at the far infrared. So we looked at 7 stars. How well did we do? Yeah. They were done before, but they weren't all resolved, right? So, depending on sort of the setup of ALMA, like your baselines and the size of the system, you may or may not actually resolve the disk itself. You may just get like an unresolved photometric point, just like all of those previous mid and far IR surveys with like Spitzer and WISE and things like that. So you may or may not resolve the disk. But I wouldn't necessarily count that as pre-knowledge of the system, because pre-knowledge of the system, I would say, is if you have a detection in the scattered light regime. So at similar wavelengths and at the wavelengths that you're trying to observe. So how do we do? Well, we actually detected 4 out of 7 debris disks in our sample. So I think that's pretty good. Yeah, so one of these systems, we sort of reported these in stages. I reported this system in a paper I wrote in 2020 or so. This system was actually reported not in polarized light, but just in total intensity light with Sphere in a paper from 2023. These are completely brand new detections, so that's really cool. And these are sort of our non-detections. But you could say that, maybe there's something here. But yeah, I would consider that a non-detection for the time being. Okay, so before we get to population studies and trends, I'm just going to briefly go over some of the unique things that we saw in our new detections. So 98363 is pretty cool because it has this sort of a weird asymmetric structure. So you notice how like this side appears not as extended as this side. So it's kind of an asymmetry there. Interesting for dynamical modeling. 109832, I really should have little thumbnail photos of each of the disks here. But 109832, it's very compact, and it also has a very strong brightness asymmetry, which could be indicative of a warp structure. Again, something that could be caused by dynamical interactions with planets. We have 112810, it's super faint. And then we have 146181, which is pretty bright and it's very inclined. It may have a bit of a brightness asymmetry at what's called the disk ansay. Sorry, I'm jumping over slides. So like this side may appear a little brighter than this side, for example. I'm jumping slides all over the place. Okay, so again, before we get back to our population studies, let's do a bit of work in characterizing this system. So understanding what the properties of these systems are. So we're going to follow an approach described in a paper by Katie Krotz in 2024, and it's sort of an empirically informed characterization approach. So what you do here is you fit a ring or an ellipse along the spine of the disk. So think along like, the brightest portion of a disk. And you'll be fitting for a size of the disk, so like a radius, whether or not that ring is offset from center, and along with the inclination and the position angle. And something else you can do is if you have well-constrained posterior distributions for your offset, then you can also sample those to estimate an eccentricity of the disk as well. And you can also use these spine locations to place photometric apertures to measure surface brightness as well. So multi-purposeful. And this is just showing the approach that you would use if you wanted to fit like an edge-on disk versus a less inclined disk, right? So in an edge-on disk, you can almost just fit Gaussians, along the vertical profile of the disk. In a lower inclination, you're still fitting Gaussians, but then you kind of have to go in, you kind of have to follow the shape of the disk a little more. Okay, so that's the characterization approach. Here are some of our characterization results. So on the left, I'm just showing all those little black points are where the sort of spine locations are, and then the ring is being fit to those spine locations. And the properties of that ring translate into the properties that you see in the table below. So, you have your sizes, you have your offsets from center, your inclinations, and your position angles. And I was also fitting for eccentricity here as well. And then on the right, I'm showing the measured surface brightness profiles of the disks. And so right away, you notice that, you have some degrees of eccentricity, you have quite a bit of asymmetry. So, interesting stuff and on an individual system by system basis. But, remember my goal was to understand population trends or, properties of the sample of SCO-SEN systems. So let's get back to that. How are we going to sort of assess the properties of our potentially unbiased sample? Well, there's still this issue of the scattering phase function, which I brought up earlier in the talk. And I'm going to explain to you why that is a problem. So just a bit of a quick explanation on what the scattering phase function is. It's describing the scattering efficiency as a function of deflection angle of an incident photon. So let's pretend that we're looking at a face-on disk here. So to us, the ring kind of looks like this. For us to see that disk, all of the photons that strike the dust grains in this disk have to deflect at a 90-degree angle in order to reach us. Otherwise, like, any photons that deflect at other angles do not reach us, the observer. Okay, now in the edge-on view, so now let's pretend we're the telescope here observing, and we're sort of, the photons are coming at us, right, from the left. Well, now your photons can deflect at multiple different angles in order to reach us, the observer. So if your photon strikes here and we see it, it didn't have to deflect anything, right? It didn't have to deflect by any angle to reach us. Or, if a photon hit this part of the disk, it had to have deflected by 45 degrees in order to reach us. And similarly, here, 90 degrees, and so on. And so why these deflection angles matter is because the flux that you will see at a given deflection angle will not be the same as the flux you would see at a different deflection angle. And this is really different from thermal emission, because in the thermal emission regime, you mostly expect isotropic behavior. So regardless of how a photon strikes those dust grains in thermal emission, we expect the dust grains to emit isotropically in all directions. And so what this looks like in practice is that, okay, so on the right here, I'm showing measurements of the scattering phase function as a function of this scattering angle or deflection angle for different dust environments, both solar system and extrasolar. And you see here that you get much greater scattering efficiency at these smaller scattering angles than at these larger scattering angles. And so this is going back to this detection bias of edge-on disks, being much easier to detect than face-on disks, because you just have much more scattering efficiency or flux, coming from these smaller scattering angles than you do from these larger scattering angles. And so generally, when you look at a system, you're never seeing all scattering angles at once. It depends on the inclination of the system. So generally what we say is that you as the observer are sensitive to 90 plus or minus I, if I is the inclination of the system, degrees in scattering angle. So let's say this is an inclination of 75 degrees. The minimum scattering angle you'd be able to see is 15 degrees. And the maximum you'd be able to see is 165 degrees. You can never see anything below 15 degrees or greater than 165 degrees. So, this is really hard to deal with if you're trying to understand properties of debris disks, because debris disks have different inclinations. And so how do you compare them evenly? So, so what we're going to do is we're going to measure the surface brightness at the disk ansae. And so the disk ansae are sort of these points here. And the reason why we're going to measure at the disk ansae is because regardless of your viewing inclination, you will always be able to see 90 degrees in scattering angle of your system, right? So remember in this approach, the dust grains can only deflect 90 degrees, right? And in here, you will see 90 degrees only at the sort of edges of the disk, right? Which are the ansae. So if we compare at 90 degrees, if we only measure at 90 degrees, that should be a pretty even comparison across all of our systems, regardless of the inclination.
Are you pretty certain you're seeing out to 90 degrees on all these?
Yeah, so it kind of depends on the system. If you can resolve the entire belt pretty well, you can usually see sort of the turnover point, to when sort of the curvature starts to look like it's going towards the backside of the disk. But it can be more challenging for really large systems, especially if the ansae may be outside of the field of view, or if you're really edge on, it can be a bit difficult to distinguish like at what point is it actually turning around, or maybe you have some of these halo grains that are sort of outside of the primary ring of the disk, and they're just sort of diffuse and outside of the actual main belt of the system. So that is a limitation. Okay. Okay, wow, 3 more minutes. Great, so we're going to measure the surface brightness at the ANSI. And then we're going to divide by the stellar flux. In order to get similar to a fractional infrared excess, we're going to calculate a fractional scattered light excess. So I'm going to call this F ANSI F star. We're going to normalize by this factor of size of the disk or radius, because if you know flux and luminosity, intensity of light falls off in sort of 1/r² behavior, right? And we're going to determine these ANSI locations by using the sizes of the disks that we found earlier, along with the modeling efforts that were done in Katie Krotz's 2024 paper. So she did this for a lot of systems already. And to really understand if we have a good sample of benchmarks, we're going to do this sort of measurement analysis independently between SCOSEN systems and all of our other non-SCOSEN systems. And so what are our results? So on the y-axis, I'm plotting the F ANSI F star, and on the x-axis is the fractional infrared excess. And so, perhaps expectedly, you get these positive sort of trends, meaning that, okay, the greater your fractional infrared excess, or, the greater amount of dust content that you have in the system, it sort of follows that you would have a greater amount of scattered light excess as well, right? Because this is just saying you have more dust mass, and so you have more dust in the system. But perhaps the unusual thing about this is that you get this offset between SCOSEN systems and non-SCOSEN systems for a similar range in fractional infrared excess. And this offset can be as much as a few orders of magnitude. So that's not little. Like that is a lot. And so what this is kind of saying is that you must be getting a much greater contribution of scattered light than you would expect for systems that would have similar amounts of dust, assuming that that can be sort of explained by this fractional infrared excess. So it kind of seems like you have a lot more of these smaller dust grains than you would expect for systems that would have similar amounts of mass in larger dust grains. So this is really weird. This is really, really weird. And okay, so let's try to unpack this. Okay, so this is comparing the F ANSI F star with inclination. So yeah, so there was a question before about whether or not you have a bias with inclination, because the greater your inclination, the more likely you're able to detect a system. But what we see here is that yes, the higher inclined systems are generally a little brighter, but you still have quite a bit of division between the SCOSEN systems, which are all these circles, and the non-SCOSEN systems, which are all these triangles. And you can do some limited statistical analyses and show that, well, overall, the SCOSEN systems do not span a different range of inclinations than the non-SCOSEN systems do. So even systems that have similar inclinations, SCOSEN is still much fainter than all of these other systems, all of these other non-SCOSEN systems. Okay, I don't have a lot of time, but I'm just going to quickly go over observational biases. So there are probably some pretty big observational biases in the sort of non-SCOSEN sample of debris disks. The detection rate of the non-SCOSEN systems is about 40% or so. So we're probably not getting the full sense of scattered light properties from these non-SCOSEN systems that span a similar range in IR excess, because we were not able to detect them. And so likely all of these relative to other non-SCOSEN systems are probably outliers, right? We don't have the full picture. But SCOSEN, on the other hand, we have a much fuller picture, right? Because we've detected more than half of the systems. We've had an 80% detection rate. And so, our non-SCOSEN sample is probably pretty biased, whereas our SCOSEN sample is much less likely to be biased. And so that probably explains why there's such a discrepancy between the two samples, but it doesn't really explain why this range is still so large. And then let's look at a few other factors, and I know I'm pretty much out of time, but yeah, intrinsic grain properties and age. So, grain properties can give you differences in scattering efficiencies. But that's kind of weird that you would have vastly different grain properties between, the SCO-SEN systems and the non-SCO-SEN systems. Age is also a factor because older debris disks should be much fainter. But actually, we're finding that most of these non-SCO-SEN systems, which are mostly older, are actually brighter, right? So that's almost counterintuitive. And then we can also take a look at the radiation environment, so stellar properties. And this is also weird because, in the SCO-SEN systems, you get a decreasing scattered light brightness as a function of essentially spectral type or host star effective temperature, but then you see the opposite in the non-SCO-SEN system. So in the non-SCO-SEN systems, they're actually getting brighter with effective temperature, which is also weird. And then you could also look at presence of gas, and I'm going to skip over that because basically it's hard to assess that, but okay, so what we're kind of hoping for is that all of these sort of discrepancies could actually be attributed to dynamical activity or collisional activity, maybe because of planets. So maybe in these non-SCO-SEN systems, you have enhanced collisional activity, which is causing them to produce way more submicron or micron-sized dust grains through collisions, and therefore are much brighter in scattered light. So, could that be what's happening in these systems? Maybe. I'm hopeful that maybe it is, but it's still hard to determine that definitively. And I'm going to skip over this last slide because I am out of time. But essentially, I think we've started to build up this really good benchmark sample of systems of debris disks. And this benchmark sample is really important for us to be able to understand how debris disks sort of fit into the planetary formation picture and the planetary evolutionary picture. And having benchmarks is really important because we need to be able to ground any of the results that we get in future observations, such as with JWST, for example, that are resolving and imaging these systems in thermal emission, right? Like we want to be able to have a complete picture of everything that is going on. And I think I'm just going to end it there because I'm out of time. But yeah, thank you again for listening to me ramble on.
I have
Sure.
a few things, questions, but we all have this meeting we have to go.
Yeah.
But my two big points are you're probably right about the grain size distribution. That's like, especially if one environment is very tightly bound and the other one's kind of all